A very good afternoon, ladies and gentlemen. Welcome to the group exhibit Hydrogen Fuel Cells Europe here at Hanover Fairground in the Technical Forum. My name is Mona Lee. I'm the moderator for today in this format. This is unfortunately already our last presentation here. It has been a long day full of knowledge, full of information that has been leaked here. We have been discussing the future and for sure the technology behind it. Just in case you missed any of this talk, you have them on our YouTube channel. Our YouTube channel is accessible through our website. Also, there are some signages here referring with the QR code to our social media. If you want, you can tag us on Instagram. We are in 2023, so we are also adapting to the digital world, no matter what. At this time, I'm also welcoming our online guests. Hello, konnichiwa, ni hao, bienvenidos, moin. We are live streaming from the fair. Our last talk will be how Loop Energy's eFlow flow field improves PEM water electrolyzers. We'll have two speakers on stage for that. We'll have Dr. MacKinnon, the chief scientist of Loop Energy, and Dr. Tom Smolinka, Head of Department Energy from Fraunhofer ISE. Welcome.
Thank you. Not very bright. Welcome, folks. My name is MacKinnon. I'm the Chief Scientist at Loop Energy. The role I serve at Loop Energy is to kind of oversee all the new technology innovations. And I'm here to hopefully get across a wonderful new piece of data that we've collected in the last year and a half working with ISE, Fraunhofer, with Dr. Tom Smolinka. And we will go over kind of how our eFlow flow channels are helping to reduce the electrical resistance and thermal efficiency of PEM electrolyzers. So, go ahead.
Okay, yeah. So good afternoon, everybody. My name is Tom Smolinka. As already said, I'm coming from the Fraunhofer Institute for Solar Energy Systems. I'm the head of department for electrolyzers in Portugal, and I will join and support Sean in this presentation. Please.
Okay. So I'll just start with a few. I'll start with a few key findings that we've had just to set the stage for what we're going to discuss today. Each one of these will have a slide that we'll go through in a few minutes. So first of all, one of the benefits that we've identified is that our flow channels, the trapezoidal shapes themselves, can provide an improved electrical efficiency to an existing PEM electrolyzer. Secondly, in doing these experimentations, we've actually identified that the outlet temperatures of our flow channels actually are lower compared to baseline systems. So we're going to discuss a little bit and show you some data around improved thermal efficiency that we've measured with these setups. Number three, we can use that improved thermal efficiency to essentially produce more hydrogen. And we'll go through an experiment. Can you turn me up a little bit? Because I'm kind of... We're on full? All right, no problem. So I'll yell at you guys a little bit to see if you can hear me better. All right, here we go. And last but not least, we'll then go over the additive component of this, where we actually think that what we've provided for you guys to look at and review today is additive to any other further developments that you might see in the future with its membranes or porous transport layers, etc.
Well,
there you go, Tom.
Okay, so I would like to introduce a little bit to the hardware we used for this measurements to prove the eFlow cell concept from Loop Energy. And I would like to start with our, let's say, so-called baseline test. So here you see, let's say, the test rig on the left-handed side. It's kind of our working house. Even louder. I do my best, but I already... Okay, is it not good, way?
Let's have a short break. Let's have a short break. It's the cable, you're up again.
I can take the micro if you like.
Yeah.
You're welcome. Yeah, okay. So but I do not have to start from the beginning, right? So if you can go back to slide number 4, please. Okay, now here you see our technical hardware we used at Fraunhofer Institute to perform these measurements. On the left-hand side, you see our test rig where we do the performance test. Not to go into too much details here, shortly spoken, we had a test bench which is capable to work with currents up to 500 amps and with temperature up to 80 degrees Celsius and pressures up to 50 bar, which allowed us to perform this test. More interesting, on the next slide, you see the test cell or the test platform we use for these measurements. That came from another research project. That is our kind of laboratory stack design. You can say it's a stack with an active area, small area of only 150 square centimeter. And we adapted this concept to the loop flow field design. And actually the test cell, we only changed the anode side, the flow field on the anode side. So when I go to the small pictures here, you see here the small cathode side, which is more or less the standard design we used for this kind of test platform. And then on the anode side, you see how we perform this performance test and made the different measurements. On the upper figure, you see our standard flow channel, parallel flow channel. And in the figure below, you see the e-flow concept. And maybe you can see it as a small trapezoid shape, which means the flow channel is narrow from the inlet to the outlet, right? That is the main concept idea of this e-flow cell concept. More details can be provided by Sean. And of course, when you have such a performance test, we always state with a kind of polarization curve, which you can see on the next slides on these here, where we have the key finding. We measured with our test setup an improved electrical efficiency when we compared our standard flow field design to the e-flow cell concept. What you can see here is the cell voltage, which is plotted against the current densities, so-called polarization curves. On the left side, you see that at 60 bar and 60 degrees Celsius and 1 bar pressure. On the right hand, as an example, only as an example, the 80 degrees Celsius at 1 bar pressure. Higher efficiency in a polarization curve means that you have a lower shape, a lower step of the polarization curve. And here you see 3 polarization curves in each figure. You see on the top, you see our baseline. Then below, the blue polarization curve is the e-flow concept number 1, and number 2 concept is the yellow plotted line. And what you can see is we get for every current density, we get polarization curves with a higher efficiency, which means the cell voltage is lower. And when we talk about PEM electrolyzer, we would like to set rather on the high current density, let's say up 2 to 3 amps per square centimeter. And we could measure with the e-flow concept here a voltage advantage of 40 to 80 millivolt roughly. And keep in mind, all setups were run at the same inlet temperature, which means although we have a same inlet temperature, the performance is better and the temperature is lower. Also, we would expect the temperatures higher. And the reason for that would be explained by Sean in the next slide.
So first of all, I'll just call out 2 numbers here. So the 40 and the 70, I'm going to make a reference to that in a couple of slides. So with the 70 millivolt, we're approximately 1.7 times more efficient than the 40 millivolt in comparison. Okay, so I've got a couple slides coming up here that'll hopefully explain a little bit more of what we've accomplished. So thermal efficiency. All of these tests that you see here on the y-axis, it's the delta T from inlet to outlet. Along the x-axis, these are different flow rates. So close to the y-axis, we're looking at about a stoic of about 100 to 150. And as we transition towards the furthest way out on the y-axis here, where we're looking at higher flow rates, that's about 1200 stoic. So as we all know in the electrolyzer space, we are looking to run quite a bit of coolant through these systems to keep them cool. We're running water as our coolant. It's not necessarily used as a reactant for flow. We're flowing enough fluid to keep the temperature down because we're putting as much electricity into these systems as we can to produce hydrogen. So as you see here, delta T's at 2 and 3 amps on left and right, both at 60 degrees, show very similar profiles. Slightly different delta T's based on the inlet, or the current density, sorry. And in the second slide, you see exactly the same profile, but at 80 degrees. So our takeaway from these two slides is essentially at whatever current density we were operating at 60 or 80 degree inlet temperatures over all flow rates, our flow channel was more thermally efficient. And this is important from a, pardon me, this is important from a production of hydrogen perspective, because this now begs the question, well, how much more energy can we put into this system to have an equivalent efficiency as the baseline and a similar thermal profile? Whatever extra current we can put in essentially means this is how much more hydrogen that we can be producing for all of the same inlet conditions. What you'll see in the top right corner is we've actually now have, on the top end, you have a high current density. On the bottom side, you've got low current, or the 2 amps and the 3 amps. Wonderful. What we see here is we've now matched the baseline profile by adding more energy. So how much more energy? Well, at 2 amps per cm squared on setup 1, so if you recall earlier, setup 1 was the 40 millivolt improvement on the polarization curve that Tom just described earlier. We're about 7.5% more current into that system. And if you look on the right, just behind where Tom is standing, you'll see that the cell voltage is plotted against flow rate. And the cell voltages now overlap, which means we're at the same efficiency under all of those same flow rates. And this is important because when we look at the 3 amp data, we're up by about 10%. Now, 7.5%, 10%, this isn't something you might not want to write home about, but at the same time, if we look at the 70 millivolt data, where we were a 1.7 times more efficient than our setup, than our first setup, with setup 2, I've changed the color here because I'll admit this is a calculation. We didn't run this test, but if we use the same analogy we just used with the thermal profile on the right to match, we're up and around 13 and 18%. If you look at that as an average of 15% or so, this is a pretty relevant number, I would think, because you can look at it from an oil perspective and say, if you could make 11.5 barrels of oil for the price of 10, you're going to make a little bit of money in the future. So this is how we kind of look at this right now. We have an opportunity with all of the same inputs to produce more revenue from that system, okay? Now, if we move forward, we have to ask ourselves, well, what is the commercial relevance of this? I've just given you one example, but that might not be the only example. We have many opportunities for trade-off studies. As you all know, you can choose an operating condition, a flow rate, a catalyst loading, an active area, a size of your stack, and all of this is dependent on what your application is. And what we think, by looking at this data, what loop energy provides in flow channel design has essentially nothing to do with what you may invent in the future from an MEA perspective. So when we talk about improved electrical efficiency, the first two there are lower electricity costs. So maybe your hydrogen's a little bit cheaper now because you don't have to pump in as much expensive grid-tied electricity into it. Or you may look at it from a perspective of, I want to lower my catalyst loadings. If you lower your catalyst loadings, your efficiency will go back to where your baseline was, and maybe you can thrift out some uridium. So based on the previous talk, that might be a very interesting thing when we talk about scarcity of uridium in the world. Both of those things lead to either OpEx or better CapEx from those two perspectives. If we keep looking down that same line of thought, improve thermal efficiencies, well, better durability is one. And the second point there is the one I just described in the previous slide. We can add more electricity in and we can produce more hydrogen. And that's a greater revenue generator for whoever it is that owns that electrolyzer. And Tom and I have discussed this a few times. And when we look at MEA development in the future, higher activity catalysts, maybe thinner membranes, thinner porous transport layers, all of these make the MEA better, and we feel that that's additive to what we provide. So we might be 40 to 70 millivolts better based on 125 micron membranes, 1 millimeter thick coated PTLs. But when you start to thin those out, we feel that that 40 or 70 might actually be a greater percentage in the future based on what we're currently doing today. So part of this, and I'll just kind of conclude the last part of this talk, is we're soliciting for anybody that might want to work with us to develop that next stage electrolyzer. So the work we've done here is at 150 centimeters squared. It's not small, but it's not commercially large. So we're not sure if we're going to be in the 600, the 1,000 to 3,000 centimeters squared, but we are looking for partners currently to join us to understand if we have more relevance to apply. And I'll leave you with this little thought. When we think about thermal efficiency, anytime you run a fluid down a hot surface, it's going to pick up more temperature as it leads towards the outlet. This work was done on channels that were about 20 centimeters long. When we move to 1,000 to 3,000 meters squared, you could see that there might be an expectation where the temperature differential is going to be larger, you're going to need more flow rate, and we might need to use one of those different flow rates that we showed you earlier, maybe not 150, but maybe closer to 1,000 stoic. But we've got relevance across that board, and we're looking to start that work, and if you want to learn more, please come and talk to one of us. Cheers.
Thank you very much. I'm able to take questions from the audience at this time.
Is there any test about degradation rate with the flow channel and without the flow channel? And how much pressure is working on the electrolyzer? And how is the pressure profile is changing with the flow channel?
So first of all, this was just a first performance check. So we haven't done any durability work, so we can't comment just yet on what that durability looks like. But hopefully we can report out on that after we have a partner and we start doing that work. Secondarily, your second question, sorry? Yes. So with pressure, what's very interesting with these channels is we see a slight increase in pressure, but it's not a dramatic increase in pressure. And that's like any flow rate. So the more water you flow through a channel, the higher the pressure drop's going to be, and you can see that in the inlet pressure. But when you compare all of the flow rates, like we did with the thermal profile, there's a little bit there, but it doesn't appear to be something that would hurt us from like a parasitic load to turn up the flow rate that much higher that you're going to lose your benefit. But that is one thing that we would be looking at with the larger cells for sure. And Tom can comment some more.
Yeah, I can add on that. If you have in mind the pressure loss in the whole circulation loop, you can we can assume that the pressure loss, the additional pressure losses will be very, very small compared to what you have in the whole circulation loop. And to your third part of the question, we only measured the inlet and outlet pressure and have not the pressure profile along the channel, but that's something we do rather by calculation.
So thank you very much to the both of you, Tom and Sean, for giving us the latest insights on eFlow. Give them a warm applause. Thank you so much.
Thanks, folks.